Okay, area under a curve again. So far we've estimated the area under a curve by summing up the area of n trapezoids of equal height, calculated the area under a curve by using limits and the area of rectangles, and note that the area under a curve is beneath the curve above the x-axis and goes from x equals a to x equals b. So let's look for a pattern. We'll look at a couple of things. Like here's a function, right? What's the equation of this curve / line? Y is equal to 5. Y equals 5. What's the area under the curve from 0 to 1? So what's this area? 5 units. Okay, so 5 square units. How about from 0 to 4? 20 square units. What if we came up with a general formula? So if we said it goes from 0 to x, what would the formula for the area be?
5 times a plus b.
So we're going from 0 to x. 5 times x. Area would be 5x. The equation of our curve is y equals 5, and our formula for the area under the curve is 5x. Okay, one piece of information might not mean too much just yet. What's the equation of this curve?
2x.
Y equals 2x. If I want the area from 0 to 1, what would the area be? So we'll go with 1/2 base height. What's the base? What's the height? What's the area? What if we did from 0 to 4? So what's the area? Thank you. Yeah. What would the general formula for the area under this curve going from 0 to x? So, well, still 1/2 base height, right? What's the base? What's the height?
Y.
What's y? Because we have a specific function, 2x. What's this equal to? X squared. The equation of our curve is y equals 2x, but our formula for the area under the curve is x squared. Is there any relationship that we can sort of see between...
It's an antiderivative. It goes backwards.
Oops, sorry, it goes to there. 5.
It does the opposite of the derivative.
So it looks like the blank of the area function is the same as the equation of the, so the what of the area function? How do you get from here to here? Take the derivative. Looks like the derivative of the area function is the same as the equation of the line, the curve. The curve. Okay, let's take a look. Let's try one that's a little more complicated. See what happens here. So the graph of f of x equals 2x plus 1 is shown. A region, A of x, is indicated. What's the shape of A of x? Trapezoid. Or, let's go all British or European or Australian. They call them trapeziums. Kind of. Determine an expression for the area. So it's a formula for the area of a trapezoid, right? So A of x is 1/2. What is it? B1 plus B2 times H. Right? Check. Yep. Okay, so 1/2. So what's B1? F of 1. What's B2? F of X. And what's the H? X minus 1. Right. H is the distance between the parallel lines, right? Okay, so X minus 1. All right, so we can work out F of 1. What's F of 1? 3. What's F of X? 2x plus 1 times X minus 1. Okay, so what have we got in here? We got 2x plus 4. Okay. We got 2x plus 4, right? No, I put it to voicemail. 1/2 of 2x plus 4 is going to be x plus 2, right? Times x minus 1. So this will be x squared minus plus x minus 2. So here's an expression for the area function, right? Area is x squared plus x minus 2. Determine a prime of x. So what's the derivative of this? So a of x and a prime of x is 2x plus 1, which is what? That's the equation, right? It's f of x. So a prime of x is equal to f of x. Right? So there's some function if you take the derivative of that function, you get the curve, but the derivative of the function you're taking the derivative of is the area. Okay. So the area is related to, so I can see your reaction. Right? Your reaction is something like this. Okay. This ruins the moment. Where's the play? All right, here. Or it's just not connected to the internet.
It's not even buffering. It's just
Ruin the, yeah.
This was such a good moment. You're gonna have to edit the video to make it look funny.
Click on the video.
Oh, here we go. Thank you. So this is your reaction.
Oh
I take the derivative of the area, I get the function? No, we can't. No. Okay. Okay, so here we go. Let's formalize this. Because actually all we've done is a little bit of inductive reasoning, right? We've looked at 3 examples. We've said, well, for these 3 examples, this is true. Prove it. The graph of a function y equals f of x, where f of x is greater than 0 on an interval from a to x, is shown. The area under the curve of f above the x-axis and between a and x is represented by the function capital A of x. What happens if we go beyond x? What if we move this over a little bit? Let's examine the shaded rectangle. The rectangle we added has a width of h. H, that's the width of that rectangle, which gives us a right endpoint of x plus h. For a small h, you can see that we're approximately going to get a rectangle, right, with a base of h and whose height can just be represented by f of x, the left edge of this, not really going to matter. Thinking of a as the area function so far. So in other words, the area, when I say the area function so far, I mean a of x is from a to x. A of x plus h is from from little a to x plus h, right? It's the new area which we've just increased. So if we think about it, if we take the new area, including the shaded, subtract the original area, then we're going to get an area about equal to that rectangle, right? Which is h times f of x, about that. And if we divide everything by h, we get a of x plus h minus a of x over h is about equal to f of x. And we should recognize the expression on the left. A of x plus h minus a of x over h. What happens as h approaches 0? Right? Add a little thin slice. We get the definition of a derivative. Right? So the limit as h approaches 0, this thing here, that's a derivative, right? It's a prime of x. But this thing is about equal to f of x. So there's your proof. If you take the derivative of the area function, you get the function of the graph. So f of x is the derivative of the area function a of x. Therefore, if we want to find the area, we first need to find the function whose derivative is f of x. And we need a fancy name for that. So let y equals f of x be a positive and continuous function, and a of x be the area under y equals f of x, from little a to x. Then a prime of x is equal to f of x. Since the derivative of a of x is f of x, we say that a of x is the antiderivative of f of x. Okay, so the antiderivative. So in other words, given the function, because we know the function of the line, we need to find a function whose derivative is that. If we want to use a less cumbersome method for finding the area under a curve, other than summing up an infinite number of rectangles, we need to solve the differential equation, which means it involves a derivative, a prime of x equals f of x. By solving this equation for particular functions denoted by f of x, we can find the area under y equals f of x. To solve a differential equation, we need antiderivatives. Yeah. Whatever happened to uncle derivative? Example 2. So here's the graph. Y equals 2x plus 1 is shown. A region a of x is indicated. Blah, blah, same thing. Find the area under the graph of f of x from x equals 1 to x equals 5 using the concept of antiderivatives. Okay, so I need a function, a of x, whose derivative is 2x plus 1. So the derivative of what is going to give me 2x? Derivative of x squared, right? X squared. And the derivative of what is going to give me a 1? Plus x. So we got a function, a of x is x squared plus x. Its derivative is 2x plus 1. The area we're interested in, the whole area, will be the area from 5 minus the area from 1, because they're both going to go back to 0, right? So the a of 5 is the area from 0 to 5. A of 1 is the area from 0 to 1. We want, so a of 5 is this whole area. From that, we're going to subtract this area, giving us the area we want. Okay, so all we got to do is plug in a of 5. So 5 squared plus 5 minus 1 squared plus 1. Now, when I work these out, when I work out a of 5, I'm going to keep it separate, right, inside a set of brackets here, and then the minus sign, especially because it's minus, and then a set of brackets here. So we could just work out the brackets separately, right? So this will be 30 minus 2, which will be 28 square units. Okay, so that area is 28 square units. So we can work that out. You could do it as a trapezoid if you wanted, right? You'll find out the area is 28 square units. In general, if f, so we're going to get rid of the capital A for area, we call it capital F now. If f is any antiderivative of the positive function f, the area under the curve from A to B is f of B minus f of A. Area under the curve of f of x from A to B, so from A to B would be this area here. So you just figure out what's the antiderivative, plug in the value for B, and then plug in the value for A, subtract, you'll get the area. No more adding up infinite numbers of rectangles. Yep.
An example 1 for antiderivative for area, we got x squared plus x minus 2.
Oh, this is x squared plus x. Okay.
And why is that? How would you work that out?
We'll get to that. It's coming. It's a coming. Determine the area under the curve from y equals 2x squared plus 3 from x equals 1 to 4. Okay, so we know we need a function. We have f of x is equal to 2x squared plus 3. We need a function which we are now calling capital F of x, which is the antiderivative. All right, what's going to give you 2x squared as a derivative? So we're going to have an x cubed, right? Okay, what's the derivative of x cubed? 3x squared. Okay, but we want 2x squared, so 2/3, right? So we put the 2 here so we get the 2, then we got to get rid of the 3 that's going to come out. So let's call it 2/3 x cubed, right? Derivative is 3x squared multiplied by 3. The 3's cancel. We end up with 2x squared. Plus, what here? 3x. Okay, so constants are easy. Okay, plus 3x. We want the area from 4 to 1, so area will be f of 4 minus f of 1. Okay, plug in, keep things nice and separate, right? So we got 2/3 of 4 cubed minus, plus 3 times 4 minus 2/3 of 1 cubed plus 3 times 1. Two-thirds, 128 thirds. Plus, looks like we're going to have to stick with thirds. So 3 is 12, so let's go plus 36 thirds. Minus 2/3. Plus, no, minus. It's going to be minus 2, but we're going to stick with thirds, so we'll go with minus 6/3. So that way we've got everything in thirds. So we got 128 minus 8, which would be 120 plus 36.
Would it be 9/3?
9.
Is it 3 times 1, which is 9?
Oh, yeah, sorry. 9/3. Okay. Ruined my calculation. Okay, so that's minus 11. So 128 minus 11 would be 117, 123, and 30, 153. Check's answer on paper. Yes. Which is actually equal to 51 square units. Okay. Worked out nice. So given a curve, find its antiderivative. Use the formula for area that we have just developed, right? Determine area under a curve, y equals sine x from 0 to pi. So there's 0, there's pi. So it's a positive function, right? It's always above the axis from 0 to pi. So let's start off by saying, well, f of x is sine x. And I need a function whose derivative is sine x. Negative cosine of x, right? So the derivative of cos is negative sine, but we want positive sine, so we go to negative of cos x. Okay, so the area we want is going to be f of pi minus f of 0. So negative cos pi minus cos 0. So what's the cosine of pi?
Minus negative cos.
Oh yeah, sorry, negative cos 0. Negative cos 0. Okay, what's the cosine of pi? What is the cosine of pi? It's like 0? No. Negative 1. So we've got negative 1. Okay, negative 1. And what's the cos of 0? Positive 1. So minus negative 1. So negative 1 is 1. Minus negative 1 is going to be 1 plus 1. which will be 2. So the area under that curve is 2 square units, units squared, units squared, units squared. Okay. Is there more to that, or are we on to antiderivatives? Okay, this is where we're going to answer the question that was asked. So a function f, capital F, is an antiderivative of little f on an interval if f prime of x is equal to f of x for all x in the interval. Determine 3 antiderivatives of 3x squared plus 4x minus 5. Okay, so let's do 1. Capital F of x equals, so how do we get a 3x squared? Could be much easier, right? X cubed. How do we get a 4x? 2x squared. How do we get a minus 5? Minus 5x. Now what else could you stick on the end there? Literally anything. So give me anything. Plus 28. Okay, I don't know. So what's another one? Minus 3. You could be equal. I know you said plus 3, but I wanted to give equal time to plus and minus. What's another one? Plus 2x squared minus 5x minus e. Doesn't matter, right? Because e is a constant. Okay, it's constant. So, here we go. If f is an antiderivative of f, then the general antiderivative is f of x plus c. So we just write it with a plus c, where c is an arbitrary constant, right? Any constant. Could be e, could be pi, could be phi, could be 28, minus 3, whatever. So then the question asked earlier was, hey, wait a sec, like way back here, was it here? No, was it here? Oh yeah, we had this minus 2, right? When we went to work out the area. Now the derivative just came out to 2x plus 1. So the question is, when we worked out the area using this, what if there had been a minus 2 on the end? So what if we'd had x squared plus x minus 2 as our area function? How would that affect? So if you look at a of 5 minus a of 1, yeah, you'll get 5 squared plus 5 minus 2 minus 1 squared plus 1 minus 2. So minus 2 minus minus 2. You're going to subtract it off. So if that's a minus 2, still going to work. If it's some arbitrary constant c, still going to work because you add it on here, you subtract it off there. Oh, sorry, this is a plus c. Yeah, it's still the same. Yes. So then plus c minus plus c. Okay. So what you add on, you subtract off. Okay, so here we are. All right, complete the following chart. So we'll do a few together, and then I'll give you some time. You can work on some other ones. So the function is 1. The general antiderivative is x. General antiderivative is x plus c. So every one of these is going to have a plus c. I don't know how many half marks I will deduct for not having plus c's, but you will lose some marks if you don't. Well, so remember, when you're doing a general antiderivative, you must write plus c. If the function is k, kxc, no, kx plus c. Carry on. Okay, you can figure these out. So I'm gonna pause. Okay, so I'll just, the video's back on. I'll leave this up for a bit, so you can look at it, or at least have time to pause and look at it, because I'm not going to leave it up there forever. But pause, take a look at it. Just all you got to do is just do the derivative of everything that's there to see if it is in fact the antiderivative. Okay, and then we'll move on. We got 3 more examples, and we're done. Determine the area under the curve. So we did the derivative, the antiderivative of this, right? 6x e to the x squared was one of the ones we did the antiderivative for. So let's put this back to page width. Okay, so I like to start with f of x is equal to, so here's my function. And capital F of x is equal to, so we have that if we just look on the other page, 3 e to the x squared plus c. Okay, now the c is there. Okay, but again, it's an in and an out, right? So the area. So we want from 0 to 1, so f of 1 minus f of 0. So 3e to the 1 squared minus 3e to the 0 squared. Oh, wait, I forgot the plus c's. Yeah, 3 to the 1 squared plus c, let's put brackets, minus 3e to the 0 squared plus c. Okay. So now we remove the brackets. We get 3e plus c minus 3, because e to the 0 squared is e to the 0, which is 1, times 3, minus 3 minus c, which is equal to 3e minus 3, or 3 times e minus 1, in parentheses, units squared. Okay, so given a function, write it as little f of x. Figure out the general antiderivative, always has the plus c. Figure out the general antiderivative. Find the area using your boundaries, right? It's going to be the area of the upper minus the area of the lower. Okay, we okay? We okay. Determine the area under the curve. Y equals negative x squared minus 4x. Okay. I don't know if we did this one, but you should be able to do this one. So we know we're going to have this, which is going to cause that. And the way you check if you have the antiderivative is just do the derivative of that. Make sure that you get little f of x. So minus 1/3 x cubed minus 2x squared plus c. Determine the area under the curve. There's no boundaries. So we're going to have to... what do we got here? Negative, let's factor out a negative x. What will that give us? X plus 4. Okay, so it opens down. It's got a 0 at negative 4 and at 0. It's quadratic. So we're going to go from 0 to negative 4. Well, our upper is going to be f of 0 and our lower is going to be f of negative 4. Okay, so we want the area, we're going to go from 0 to negative 4. So we take rightmost bound minus leftmost bound, right? So area is equal to f of 0 minus f of negative 4. All right, so what we're going to do is plug stuff in. Negative 1/3 times 0 cubed minus 2 times 0 squared plus c. Minus. And just be very, just like do this, right? I mean, I know it says it's just 0, right? But show the substitution in. Okay, not for me, for marks. Don't do it for me. Do it for the marks. If you don't show the substitution, just get in the habit of always showing the substitution. It makes it easier when you're doing problems later on. You don't try and skip steps, okay? Which later on might cause more problems. So negative 4 cubed minus 2 is negative 4 squared plus c. Okay, so how much are we going to show here? Not much. So this is 0, this is 0. We're just going to get c minus. Okay, that's negative 64. That's going to make positive 64 thirds. And we're subtracting, so it's going to be minus 64 thirds. Okay, so watch that. This is going to be positive 16. This will be minus 32. Then the minus here is going to make that plus 32, which is 96 thirds. And this will be minus c. So it's basically just 96 minus 64, right? Which is 32 thirds. Square units. Okay, so 32 thirds. There's online area under the curve calculator, so if you want to check stuff, just type in online area under the curve calculator. Right, and you get to enter the curve, you get to enter your boundaries, and it'll calculate it for you. Wolfram has one. Yes, you can use Wolfram Alpha, but Wolfram has a standalone online area under the curve calculator. All right, this is the last one. You beat me to it. I was going to say this is the last one. Determine the area under the curve of y equals 4 minus 4 over x from the x-intercept. We got to figure out the x-intercept. Oh, it's 1. To x equals e squared. Okay. So we should figure out the x-intercept, or we should just show that. So x-intercept, you're going to set y equal to 0. You get 0 is equal to 4 minus 4 over x, and you can just say x is 1. Right. I mean, you could go through a whole pile of pain, or just say x is 1. Okay, so f of x is 4 minus 4 over x. Capital F of x is 4x. All right, what is that? Lawn. Lawn. Forlorn. 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 Okay, when we do an antiderivative which involves lawn, we throw absolute value sign around the x. Okay, just to say that it's got to be the absolute value of x. X has to be positive. So our area is equal to f of e squared plus c, right? Now, I mean, if you're doing an area calculation, you leave off the plus c. It's not a fatal error, right? Because it's just it goes in, it comes out, right? So it's like your float. You don't count your float, right? It's in, and then it gets taken back out again. So, but let's throw it in. Okay, what do we got? 4e squared minus 4 ln. I can remove the absolute value because e squared is positive, right? Ln e squared plus c, we like, so plus c minus f of 1, which is going to be 4 minus 4 ln 1 plus c. So 4e squared is 4e squared. Not much you can do that, but what's the ln of e squared? Yeah, so it's 2 ln e, which is 2 times 1, and then times 4, so this will be minus 8. Okay? Here, we'll put in more detail. So the ln of e squared is 2 times ln e, which is 2 times 1, or 2, so minus 4 times 2, plus c, removing brackets, minus 4. What's the ln of 1? 0. So minus 4 plus 0 minus c. Okay, so since ln 1, and then ln of e squared, right, that's just 2. Okay, so we got 4e squared minus 8 minus 4 minus 12 plus e minus c. Unit squared. If you like, you can factor out a 4. It's not, no, there's no deduction for not factoring or for factoring. And